introduce you to Hosni Adra from the greater Chicago area. There's feedback from your mic. There we go. I'm really excited to introduce you to Hosni Adra from the greater Chicago area. He's a partner and founder of Creatisoft since 1992, over 30 years in digital transformation and artificial intelligence, machine learning, and deep learning. A little bit of background on Hosni. He has, again, over 30 years of experience in digital twin implementation and automation. He's the holder of multiple patents in simulation and digital twins. He designed over 200 warehouses, 75 manufacturing facilities, and more than 25 services using the digital twin. And even more than that, for the last 20 or 30 years, he's had thousands and thousands of his packages of simulation being sold. His passion is to empower the digital twin with AI to help the worker be more productive and improve efficiency in operations. His clients are global. He's implementing in just all around the world, US, Canada, Europe, Asia. And in his spare time, he does some martial arts. He's a martial arts instructor and an avid biker. Take it away, Hosni.
Hello, everyone, and thank you for joining us. So today we will dive into the world of digital twins and discover how they can empower your workplace. We'll explore how you can leverage them for real-time optimization and unlock their full potential by integrating them with AI and machine learning. As we move forward with the webinar, I'll address misconceptions and realities surrounding digital twins. We'll uncover the tangible benefits of adopting a digital twin and also shed light on the limitations you should be aware of and expectations you shouldn't set as you proceed with the implementation. We'll explore the connection between AI and digital twin technology with specific focus on machine learning and deep learning. So as you integrate the digital twin with AI, ML, and DL for deep learning, you can accurately calculate the cost of SKU, manage your S&OP for the entire operation, and enable digital twin shadow. The digital twin shadow enables you to observe the live operations from virtually anywhere by combining data analytics and visualization tools. All of this is powered by continuous real-time optimization, constantly analyzing the operation and using the twin to enhance and optimize processes on the fly. So the digital twin from an industry perspective is essentially a virtual representation of a real world environment. Many people view it as a mere replica, which can take various forms such as an image, an animation, a simulation of the processes, or any other representations that closely mimics the actual physical environment. When you look at the picture with the two planes on the bottom right, and question what the image actually represents. The representation may be more than just the image of the plane. It can encompass a broader scope, including aspects like how the plane operates, its performance during flight, and its flight characteristics. In a digital twin context I'm presenting today, the twin is not limited to a static image, but encompasses various data and simulations, optimizations that are related to the aircraft's behavior and functionality. The confusion often arises when people think that an image alone can enable real-time optimization, or an animation represents the true state of the operation. We'll clarify these conceptions as we go along. What's crucial before you start this journey is to define your ultimate goal. If your goal is to simply provide a visual representation, then concentrate on the pure visuals. While if your intention is to perform detailed analysis and optimization on real-time data, then concentrate on using the proper tools to help you achieve that. So if you look at the digital twin environment, I classify digital twins as really four types of twins. The visual twin is the basic level of digital twin technology. It's a pure visual representation or animation of the operation. These can even be viewed in 2D and 3D. You can have them through virtual reality glasses and goggles. You can combine augmented reality into them, making them just visually appealing. However, at this stage, they remain primarily a visual representation. For instance, an architectural rendition of a building qualifies as a digital twin. An animation of an automation line is a visual digital twin. They are essentially the visual depiction of a real-life system, but cannot be used for any analytics or validation of the system. So we move into the randomized twin, and that's taking the digital twin one step further and introduce randomness and incorporate constraints into the twin. So we are now moving beyond mere visual representations and adding analytics to the twin. The animation generated from the representation reflects a dynamic state, which opens the door for analysis and validation within the twin itself. This added layer of complexity allows for more advanced use cases and a lot of valuable insights that you would have on the operation. So note that a randomized twin, based on its name, it purely relies on randomized data, and it's based on distributions and averages that are provided, that provide you a way to analyze various factors. But the randomness creates a wide range of scenarios. Once you add multiple input data points, the problem space grows, and optimizing the system becomes a constraint. The data set imported is now randomized, which means it does not represent the current state, but a variation of it. So the randomized state is not able to optimize in real time. And remember, randomness cannot be optimized. So now we introduce the data-driven twin. And in the data-driven twin, data takes the lead in shaping the twin's functionality. At this stage, we enable data to influence the behavior of the digital twin, shifting from random inputs to a more deliberate and behavior-driven approach. The twin will be defined based on operational constraints in data that is integrated into the behavior. The data is not randomized, but an actual representation of the current state. The twin will be able to replicate the specific behavior of the operation and optimize the actual data set to improve the system efficiency. Taking it one level further, and the AI and the learning twin is a complete and accurate data-driven twin that actually is enhanced by AI, machine learning, and deep learning. This is actually the main focus and main objective of a digital twin implementation. The generated twin should be able to use AI, ML, and DL, along with system constraints in order to provide an accurate representation of a real-life system and performs real-time dynamic optimization and analysis. And I emphasize that on the word real-time, where it's going to react directly to what's happening within the environment itself. So if we took a very simple video and, oops, excuse me there. So this is a sample video of a twin, and it's just purely an illustration. We're using a warehouse in this case as the illustration. You will notice that it's highly visual. Its usefulness may span the spectrum from a simple visual animation to an authentic representation of the warehouse with spatial and operational constraints. The concept is applicable to virtually any environment. While we're showcasing a warehouse here, the application can extend to other contexts. The essential distinction lies in the level of representation that is used. In visual representation, you'll witness an animation of the flow, whereas in a genuine data-driven representation, every bin and every movement accurately reflects what's happening in reality. So by thoroughly examining each one of these elements, you can gain insights on what's stored at each location, what each person is handling, their activities, the items on the conveyor, and the reason conveyors are slowing down. These aspects all contribute to the comprehensive representation of a data-driven twin. Again, this is the same concept that you can apply to any environment and any industry, as you will see shortly. So now a lot of you will say, well, what is the true difference between the traditional simulation environment that's used today and a data-driven digital twin environment? So we covered the 4 types of implementation, and let's create a clear differentiations between the two, between a traditional simulation environment and a data-driven digital twin implementation. So if you examine a traditional simulation environment, you're essentially focusing on the left side of the screen. It's either visual or based on randomness and distributions only. Distribution, again, will drive the behavior. They define the constraints. They have the failure rates, the call rates, the cycle times of the machines, the process flow, and so on. But randomness and distribution will drive the model and will drive the behavior. So due to that inherent randomness in the data, you'll constantly hover around 90% accuracy of the models when compared to real-life systems. And it's challenging to optimize outcome in real time when dealing with randomness. So when you input random data into an optimizer, the resulting optimization will be based on data that does not accurately represent your current operation, especially, as I mentioned, when you're dealing with real-time systems. So on the other side, if you look at a data-driven twin, the model encapsulates the true behavior of the operation. Instead of using random data, it relies on facility and operational constraints coupled with real-time, non-randomized data set for accurate representation. As an example, in a manufacturing setting, you have consumer demand, you have routing, you have bill of material that vary all the time. In a call center scenario, for example, you've got call times, you've got type of elevation of the calls, the workforce, that will vary. So yet the manufacturing constraints do not change. The call center constraints do not change. The number of mills, inspections, number of phone calls you can have, the number of phones, the number of operators. So all of these are constant within the operation. So the routing on how you produce the widgets doesn't change. The equipment, maintenance, and failure rate do change. But that change is based on what is running on those machines and how they wear out through time based on what ran through them. When all these constraints and physical characteristics drive the digital twin, model accuracy increases to more than 99% when compared to real-life system. Now I can seamlessly integrate this model into my optimization framework. I can use it to figure out how to rearrange call schedules for maximum efficiency, to optimize the workload, and ensure that all required materials are in place precisely when production needs them. So if you look at that, this is purely real-time optimization for just-in-time manufacturing. So the primary distinction lies in the fact that I'm optimizing using genuine, non-randomized data that accurately represents the operations through definition using behavioral constraints. So we'll address how we achieve that behavioral constraint in a second. So we have talked a lot about AI in this in the webinars, and a lot of the other presenters have mentioned AI heavily. The way we see AI in the digital twin is slightly different in the way it is applied. So one of the things that I always see in the industry is that AI is a term that is often used today, and it is becoming a very popular buzzword. Everybody wants to do AI, but most of us don't know how to properly use it, and a lot of us are purely afraid of it. So at its core, it consists of a set of algorithms implemented within a computer system. What sets AI apart is its ability for these algorithms to significantly run faster and at a much faster rate than a human can, enabling it to drive that real-time decision-making process. The challenge lies in the fact that AI represents itself in various forms. Some of them are commonly used in current technology landscape. Some of them will show up in the future, but not all of these aspects are truly usable in a digital twin environment. Machine learning is very crucial. It is an important aspect of digital twin and learning from historical data sets. So in the context of the digital twin, historical data becomes the driver of what we're going to feed the system in order to learn that historical behavior of the operation. So keep in mind that if the historical data is not there, the digital twin can actually generate a data set for you, especially since the twin is a highly accurate representation of the real life operation. The data is then used to allow AI engine to start learning the behavior and the relationship between the different entities within a system. The machine learning engine can now learn how the components interact, what makes the material handling component operate, and all the intricacies of the operation, whether that is a function of a person, a robot, or a piece of equipment. So if you take that to the deep learning aspect, that's when you take multiple neural networks and provide a solution that's way more complex than traditional problems. So this is where you begin integrating the cost analysis, scheduling, workforce management, material handling, inventory, incoming calls, bin sizes, and other operations that you would have. All of these become part of that deep learning environment. And the AI model now is going to encompass the overall operation, not just a segment of it. So these are the various aspects in AI. So there are some other aspects of an AI that like language, natural language processing, and computer vision, and other aspects like expert systems and so on. But they all don't apply as much to our digital twin technology. So what we're going to concentrate is machine learning, deep learning, and in some cases, we're going to use computer vision to help in the implementation itself.
So Hosni, a question just came in. So because you mentioned IoT and hooking up different devices in your system, that you provide that overall shell. For the IoT, would there be more applications for AI in the IoT and linking to your system and feeding it information?
Exactly. There is definitely a huge part of IoT in the implementation, as you'll see in the upcoming slide. I actually covered that and connected to the digital twin. You need to get as much data into the twin, and the more data you feed it, the more accurate it's going to be in representing the operation and providing that future state and optimization. So you're just a few steps ahead of me. So the approach primarily utilizes AI through machine learning and deep learning. When we apply operational settings of the facility or the plan of the warehouse, you include pretty much all of the input into the operation. This could be tooling, raw material, water, energy consumption, IoT devices, anything that you actually use within the operation itself. So the dimensions and the spatial representation of the facility also is a factor and is a constraint within the system. So within the context, we consider the presence of personnel, processes, data, and technology that drives the operation. And the overall objective is to process and manufacturing a product and provide it to the consumer in time. So it's not delayed and it's on schedule. So that's really what we all strive for, regardless of what industry we're in. So a quick note on the data to be used, and we talked a lot about a lot of data inputs. It's extremely important that the data must be correct and represents the actual operation. The problem arises when AI learns from the wrong data set, and based on that, it will provide inaccurate analysis of the optimization. So the data that we're going to use to feed and learn from is going to be a critical part in the component going forward. So depending on the variance sequences and the learning systems, we'll actually feed the AI engine with whatever comes out from either the machine learning and the deep learning engines in order to provide that real-time operation and real-time analysis of the system as a whole, not as just an independent entity by itself. So let's go to simple data, the connectivity of a digital twin, what kind of data input you would need, and how all that would tie in together. So we established the connections to various data systems based on availability of the data. If you have IoT devices, for example, then you can actually connect to those IoT devices that will feed you information on the status of the different equipment, how much power consumption they're using, whatever that IoT device is going to give you as information on the actual device itself. Remember, this is real-time data coming in into the digital twin, and I'm using that data to provide that optimization. For any given operation, relying on a single system offers a limited view and really does not provide you with a comprehensive and perspective of the operation. Just going to show you what that system is actually doing, not what the overall system and how the overall operation is performing. So if you look at, look into warehouses, you will have a WMS system, a warehouse management system, you'll have a warehouse control system, you'll have a warehouse execution system, you'll have the HR system, you'll have the IoT devices system, you'll have RFID, whether passive or active, you'll have your autonomous mobile robots or AMRs, and so on. And they're all material, there's a lot of other material handling that's actually responsible for the operation of the warehouse itself. Each one of these systems is providing analytics for their components, how efficient they are, but neither one of them is providing the limitations they are imposing on the overall operation. So just because I can get the item from point A to point B within 30 minutes or within 5 minutes, it doesn't mean that it can be consumed at the other end at that rate. And it doesn't mean that it's not going to cause an issue downstream for the operation. So connecting to just one system provides you that limited view of that system alone, and this is not what we're after. We aim for a comprehensive representation of the operation. So we establish connections to multiple data systems and collect all the data together, drive it into the digital twin, so we can provide that comprehensive view of the operation. That data is now used to enhance and optimize the operation in real time using what the digital twin have learned and what the AI engine and the rules of the operation are going forward. So in terms of location devices, as I mentioned, you can do passive or active RFID. You can use a GPS system. So we do have actually unique interactions where we can filter a lot of the data out and feed the digital twin just the data required to actually allow it to utilize that. It will also create a relationship between those entities. So as an example, in an office setting, let's say you tag the chair and you tag a room. When I go in and move the chair from a specific room and take it to another conference room, for example, the system understands that the chair doesn't move by itself, and it requires me as a person to actually make that movement. So that relationship is already built into the system, and the RTLS system now provides the twin with the identity that says, me moved the chair from one location to another, and I left it there, I left the conference room, and I did not return the chair back to where it was. That is just a simple representation of how that relationship actually comes in. So our focus is, we focus mainly within the four walls of the operation, yet you can actually take it outside, and you can start connecting it to the overall supply chain if you connect GPS system or other external system that feed into that twin itself. So we should always consider consumables and anything that is used within the operation itself, whether it's tooling or other components. Some of them are going to be fed through IoT devices. These elements are sometimes overlooked, but if we're truly aiming to optimize the cost of SKU and enhance the efficiency of the operation, we must include consumables as an integral part of the operational environment. Another factor that is often overlooked is the fatigue factor of the worker. Recognizing that people won't consistently perform at their peak efficiency throughout the day. So when we combine all these elements, we actually truly represent an accurate representation of the plant, the warehouse, the call center, or any service facility. The key element there is that we're looking at the operation in terms of processes and activities, regardless of the facility type. The same implementation will apply. The constraints and behavior might be slightly different, but the implementation pretty much stays the same. So just a quick note for everyone in the lean side that's performing value stream mapping. The value stream map can now be dynamically generated based on the state of the operation. So all these post-it notes that you have on a board now become digital, and the contents of these post-it notes, from efficiencies to OEE number, overall equipment effectiveness, and others, are actually dynamically generated by that digital twin. And you can also look at that change through time and see how the value stream changed and based on the improvement that's actually being made. So one thing to note is that I know we mentioned a lot of data, but don't use that data set requirement as a showstopper or something that you can never get. I'll explain how you get the data, and remember, once you have the twin is going to help you actually achieve and generate some of that data that is missing in the implementation. So let's take it one step further and go through how we break the digital twin into multiple sections and implement it. So we do have the physical component and the physical side of the twin. This corresponds to the actual facility, the number of equipment you have, the type of component, the size of the facility, how it's laid out, the walls. If you have in a manufacturing setting or a warehouse settings, you set up monuments or machines that once you set up, you cannot move. So these become physical aspects of the operation itself. Think of it similar to Google Maps. We all used it, and the actual physical representation is the map itself. The roads, the speeds, the lane capacities, the traffic lights, all these are there, and they will always be there. They don't change as much. So once we have that physical representation, we introduce the dynamic component that is part of the data set itself. So this is where we introduce the actual data that's coming from the operation. We also introduce external conditions and seasonal fluctuations within the operation. If you don't include those, then your data and your digital twin is going to be very static in the way it provides data. You have variability in the consumer demand and what's happening outside of your implementation. We have to drive that in order to provide the true representation of what I need to do today to improve my operation and constantly move it forward. So returning to the mapping and the Google Map analogy, just as the GPS system will automatically reroute you if there is an accident or a road is blocked down the line, the only difference between the two is instead of relying on a map, I'm actually relying on the digital twin representation of the facility and the physical characteristics of your operation itself. So then we incorporate other elements like consumables, costing, just so we can get the pure SNOP. And these are all pivotal in making sure that we have a true representation of the output. So all this data set will actually go into the AI system. So the AI system will basically go through testing. It makes sure that whatever solution the AI engine is actually generating goes through the digital twin and is validated through the digital twin before it tells you that this is a solution that you should use. So if the machine learning environment and the AI engine comes up and says there's going to be a bottleneck two hours down the line, that scenario is actually automatically run on the digital twin. It's validated on the twin to make sure that that condition will actually occur. And then it is presented to you as an alert to say there's going to be a problem downstream and you should do something about it. So at the same time, it applies to scheduling in exactly the same way. The AI engine is going to come up with a schedule. It's going to come up with real-time work instructions. And those could be directly applied to the operation. But before you do that, it has to run on the twin. It has to be validated that the twin actually is going to benefit from these changes before you actually know about them and start implementing them. If you don't follow that step, then you're purely relying on the AI engine by itself without any additional validation of the twin, from the twin and from your operation and how it runs. So now based on that, I can calculate the cost of this queue. That encompasses the whole operation. I can actually generate individual cost for the item as it progresses through the flow, and whether it incorporates subassemblies or it has call elevation, or it requires in a healthcare setting in elevation in somebody's case to go to surgery, for example. So the other aspect is you actually get that digital twin shadow, which is essentially the live representation of the operation. So you can access it from anywhere, and you can always get a real-time view of what's happening within the operation. So this capability is very significant because it allows you to be home or anywhere on the beach somewhere, open your laptop and connect through to the system and actually see and feel the operation as if you're there. You can actually point to an item and identify what that item is. And if this is a SKU in a warehousing, it'll tell you this is SKU 1, 2, 3. You have 3 boxes and 6 eaches. The boxes are a set of 12s. It's been in the location for 3 days, 2 hours, and 59 minutes as an example. And the next pick is going to be in 23 minutes from now. So these are all data. This is all based on the data that you have. It can actually tell you which person is going to end up picking it and going into that level of detail. So also you've got the alert system, where if that's going to basically play a very important role in the implementation. When there is a problem, it's going to alert you, and it's going to give you an alert level to identify how bad the situation is. And at the same time, if everything's functioning properly, you need to know that everything is good and you can relax. So that's really the main aspect of that alert implementation that we should always have. So if there's a potential issue downstream, you would receive an alert. It will also give you a prescriptive solution to say, if you have a bottleneck downstream, since it understands your operation, now it can tell you, you have to rearrange your workflow in that specific way, or you have to add another person, or you have to get that fork truck to move the item, or you need an extra manager or an extra supervisor in a call center setting. So these are all things that will come out of the predictive analytics and the prescriptive aspect that will give you the problem, but it's actually giving you a solution of how you fix it going forward, especially that it knows everything about the operation at this point. So the same applies to maintenance. So it's definitely a necessity in every operation and every activity that you actually go through. Scheduling when maintenance occurs is very critical to the overall operation and how it runs and the overall efficiency of the system. So you want the operation to run as efficient as possible, but now by having that AI, deep learning, and machine learning in the system, maintenance can now be scheduled ahead of time to reduce the impact of the overall efficiency. So this is not saying that the machine is normally going to be, it requires maintenance, let's say, every 5 days. What it's going to do is say the machine has processed these specific items that actually wear it more than the normal processing. So now it's going to be serviced in 4 days. And based on your schedule, that machine is not going to be used for 2.5 hours at 3 o'clock today. So now I can actually schedule that and schedule that maintenance at 3 o'clock without any impact on the efficiency of the system. I don't have to take the system down or create a bottleneck or a delay within the system in order to achieve that and complete that maintenance. So that's really how it plays out from a maintenance aspect. Of course, from a workforce optimization, I did mention that. That's really where it's going to tell you how many people you're going to need today based on what it knows the operation is, and that's where seasonality and external factors would actually come in. It's going to give you based on each zone that you have within the warehouse and tells you need 5 people at this zone and 3 people on the other. That applies to the robots. If you're using AMRs and guided vehicles, it actually will tell you how you need to adjust these so that you get maximum efficiency out of these systems. So basically, the simple path forward, we're going to take on one side of the equation, you have your suppliers and your customer demands and all of the components that actually feed your operation. On the other side, you have what you get from the twin, which is scheduling, live optimization, that visualization aspect, cost of SKU, and so on. So all that is going to be driven through that digital twin, and is going to be validated through the digital twin. At the same time, it's going to provide you all the metrics that you need in order to run the operation. So one of the key things that I always mention is external conditions, and people would say, why would I need to worry about external conditions? I'm only worried about my facility within the four walls. That's not true. External conditions have a huge impact on your operation. So you always have to classify them, and when they do come in, the engine will identify these as off conditions. They're not your normal day-to-day operation, and they will treat them this way. So if that happens later on, it will actually learn from that state, and it will allow it to represent and give you the optimization based on that condition.
So a follow-up question on that point, just trying to get some questions in.
Sure.
From a demand perspective, so if you have a change in demand from the sales team, or there's a new launch for a product and they think that there's going to be a change, how does the digital twin take that into account?
So that will be purely a representation of the data coming in. So you will identify in the data set that there's a new product launch that you're going to launch, let's say 3 weeks from now. There's going to be a bill of material that's going to be in your ERP system that's actually defining how the flow is going to be. You have your routings. So the twin now will start to plan ahead. You've got your demand that's actually changing. All that is actually feeding into the system and providing that optimization going forward. So these are all integral parts of how the twin actually evolves. And if that product eventually becomes part of your natural product that is developed, then that is produced, then that's just going to be scheduled just like everything else. The key is, this is a hands-off type operation. You really do not have to do anything on the twin itself to support that. And that's where we talk about self-adapting twins, where they can learn from the data that they actually are being fed and understand that there's a new SKU that you're trying to produce. There's a new routing that you're actually setting. There's a new person that you hired. So these are things that are understood by the twin from the data set that's being fed into it, and it's passed directly to the AI, machine learning, and deep learning to identify that future case. And it's very common in the industry. If you put in a digital twin where you're constantly working with it and you're constantly modifying it because your operation is changing, then you're putting more time into fixing the twin than you're actually benefiting from it. And the twin will always be behind, which means you get nothing out of the solution. So that's a very important aspect of the implementation. I'm not saying that the twin is totally self-adapting. If you add, for example, 3 sets of racks in the warehouse, it knows that you added the locations, but you have to give it more data to identify where those locations are. So you have to give them maybe an XY coordinates or some additional data so it knows where they are within the system and create pathing in the background. But that's a critical aspect of the implementation itself.
Thanks, Hosni.
So I'll go quickly through the timeline. We basically go through understanding the flow, the value stream mapping, and the implementation. That's really take you to the 90 days plan. The week 2 and through 4, we start understanding the operation itself, start the modeling cycle, and drive consumables into the system. Then we go into the production line and actually complete the modeling, get the AI, and start actually feeding data in the AI from a constraint perspective and from a behavior and rules within the operation itself. Then you go into testing and making sure that everything is working and everything is set up and running the way you want. You define what kind of views you want to see from the digital twin at that point. And then you proceed in the last 3 weeks really to validate and making sure that it's actually performing the way you want and it is accurately representing your operation. just keep in mind there in that 90-day plan, if you have 2 million square foot facility, that timeline may not be 90 days. You'll have to actually take that into consideration as you build up. This is for a medium-sized implementation. In some cases, you will actually take one section that has a high ROI. You will take 60, 70% of the operation and actually implement that in the 90-day time period, and then expand it later on as you improve the operation itself. So just quick things on the benefits of what you get. It's very flexible in the way it applies and actually show you the data. It's going to show you the data that you need based on the actual situation that's at hand. It is a one view, one system. By connecting all these systems together, now the twin actually represents the true view of the operation, and it's giving you that interaction between all these systems and how they're impacting each other. So of course, cost control, everybody worried about cost, and this is really why we do this whole thing, is to really reduce the cost of the operation itself. So this is where that cost efficiency becomes important, and that's where we allow the data itself to tell us how efficient and how the operation should run in order to reduce the cost. So you can never overstate how important the data is, because it speaks for itself. It doesn't have an ego. It doesn't care what kind of experience I have. It just says it the way it is. So if it foresees a potential bottleneck, it's going to let you know. Even though somebody might say, well, this is not going to happen because yesterday the same thing, I saw the same thing and it did not happen. It's just the data looking at other conditions and other scenarios that I did not know about, and it's going to define a bottleneck. So it provides you that control over the operation, and it's going to give you those set of tools that actually determine how effective your operation is. The other thing is it's going to give you complete visibility over the operation. So in general, people tend to perform much better when they know that they are being evaluated based on objective metrics rather than someone's perspective or someone's view of how they operate. So by looking at the metrics and knowing exactly where they stand, they know how well they're operating, and they know that their level of productivity is where it needs to be. So, of course, the key is to get that ROI in less than 3 months and actually drive the overall system. So just a few things on the roadblock to success. I'll go through these quickly since I'm almost out of time. One is corporate culture, and you've heard this many times with other speakers today and yesterday. If you're going to do a digital twin implementation, it's got to be driven by management all the way down to every single employee. It's not a question of why you would do it, or no one should question why you're going that route. So you have to actively drive the initiative and make sure that everyone is on board as you're going through. Lack of data is always an excuse. It's a showstopper that people throw in because they will say, well, I don't have enough data. Well, guess what? You are running the operation today. So if you're running your business, you do have data. If you're running your business without data, then you're probably out of business today. So everybody has data. You might store it in different locations, but you have data that actually will help you drive the twin. So that's never an excuse that should be taken as a roadblock to success. Unfortunately, a lot of people do. The transition step to the digital twin is important. Again, it's making those decisions, and that's a cultural shock to everybody. Now a machine is telling me what I need to do, and it's helping me do my job better. I know more. I've done this for 30 years. You're not going to tell me that the machine knows more than I do. I guess what it does. So it uses data to actually validate that. So I'm going to use that data set to actually help me. Instead of going against it, I'm going to use it as a tool to help me achieve what I want. And of course, the digital twin tool set, make sure that your tools that you're using is able to achieve that behavior. It's able to run that data-driven environment. It has enough power to actually run those analysis fast enough so you can get the data in real time. So these are all key things that we look at from an implementation point of view. And just a quick note on where the technology is going. Definitely self-adapting models is going to grow in the way it works, where the digital twin will learn from the data and evolves itself into that operation. And that's going to provide you the full hands-off operation of the twin. And of course, expanded AI, ML, and DL to provide better prescriptive and better solutions for the problems that you have.
Hosni,
so that's
fantastic presentation.
Thank you.
We have a lot of questions.
I ran over.
We only have about 30 seconds. There is one question I want to get to. If you stop sharing the presentation, that'd be great. And the question is, can the digital twin integrate applications of a warehouse management systems that use Laravello.net or companies with quite a number of branches and can ensure network communication problems?
You can definitely use that to basically support that type of environment. You can, again, the digital twin doesn't have to be just one warehouse within the four walls. You can have a digital twin for each one of the warehouses and a digital twin for your overall operation that's actually overlooking everything, right? So it depends on the level of detail that you want to get. But that actually has been done. Not sure if it was done for that specific type of WMS, but we have done it for similar WMSs that are network connected, and then they do have their failures in between. Normally, we recommend that for every warehouse, the implementation is actually on-prem and where you have fully access. It's a real-time system, and it needs to be real-time, and it needs to be active and connected.
Excellent, Hosni. Really enjoyed the presentation. I think we could talk for a couple hours on this topic. I really enjoyed it, and I know that everyone else did. Thank you so much. And during our panel discussion, you have more chances to ask Hosni questions and the rest of our team here. So thanks, everyone. And thank you, Hosni, for putting together this fantastic presentation.
Thank you. Appreciate it. Thank you, everyone.
Thank you. With that, at the top of the hour, we will come back with Excellence with Paul and Himanshu. So please join us at the top of the hour. If you have questions, you can send me an email, jdevries@consultingeig.com, or Hosni directly. I think there's a few more questions in the chat. Please do feel free to reach out to us and or Brian through what he sent in the email, and we'll get those questions to Hosni and back to you. Again, thank you so much for your time, and see you at the top of the hour.